Okay, which one of these things can be considered chemical solutions? Yeah, Eric. Windex. Yes, perfect. Chemical solution. What else? I see water, I see grass, I see motor oil, makeup, Windex. What other thing can be considered a solution? Yeah, Grace. Yeah, motor oil, and there's one more. The makeup, right? There's 3 things here that can be considered chemical solutions. 1, 2, 3, right? Why is water not a chemical solution? It's a substance. Yeah, close, yes. Is there anything mixed into water? No, water is a pure substance, right? It's a pure substance. There's nothing that's mixed into it, okay? It's going to be what a lot of solutions are based out of, right? A lot of solutions are made with water, but water itself is not a solution. And then why is grass not a solution? It's not a mixture. It's not a liquid, right? It's just a thing. Okay, so yeah.
Is that solution that's called oil?
Yeah, this is like what you put in your car. Yeah, like oil that you put in your car. Yeah. Okay, so solutions are homogeneous mixtures of 2 or more substances. What does homogeneous mean?
They're the same throughout.
Perfect. It's the same throughout. So solutions are homogeneous mixtures, okay? Make sure that you don't feel like you have to write down every single word that's on here, right? Shorten it down a little bit into your own words. But homogeneous mixtures are also called solutions. So they share a name, okay? And it just means that things are dispersed evenly throughout that mixture. Okay, so some defining qualities of the solution is that it's the same or uniform throughout. And it means it has the same concentration throughout. So if I take a sample at the top of my container, and I take a sample at the bottom of my container, they should theoretically have exactly the same concentration and exactly the same makeup, okay? Usually when we think of solutions, we think of a solid being dissolved in a liquid. So what's like an easy life household example of a solid being dissolved in a liquid? Salt water? Yeah? What about other things like that you drink? Yeah, like Gatorade powder being dumped in, lemonade, Kool-Aid, all of these things that you mix, right? Crystal Light, those are all examples of a solid being dissolved in a liquid, okay? What about if we have liquids dissolving within one another? Can you think of a household example for that? Right, and when we think about dissolving, there's a couple other properties that go into that, but dissolving or mixing, right, liquids that mix together to form one coherent solution, what would be an example? Yeah, Eric, what do you think? An Arnold Palmer, good. So lemonade and tea mixed together and to make a drink, right? If you pour cleaning pine sol into water, it makes a soapy solution, right? If you mix chocolate milk and white milk, right, to make it less chocolatey, which why would you do? But those are examples of liquids being dissolved in liquids, right? They're mixing together. And then a gas dissolved in liquid is a little bit difficult to think about. Can anyone come up with an example for that? When a gas has been dissolved in a liquid? I really can only think of one really good example, but it's really common. And okay, so let's see. I'm going to try to get you to get there. If the gas becomes no longer dissolved, then this product is not as good. Not paint. Is that what you said? Paint? Oh, propane. No, because the propane smell, is that what you're thinking of? That happens when the propane evaporates. Good idea, though. So when the gas is no longer dissolved, the product is no good. What'd you say? Pop. There we go. You've got bubbles that are evenly dispersed throughout your liquid, right? Your gas has been dissolved in that liquid. And when it's no longer dissolved, the bubbles go away and it's just not as good, right? That's an example of gas being dissolved in a liquid. Okay, so some properties of solutions is that they have small particles that are evenly distributed and theoretically they won't separate. Theoretically, right? In perfect solutions, they won't separate. So I give the example of when I make chocolate milk, it's like a little milk with my chocolate syrup, right? It's like a little bit and a lot of chocolate syrup. And so what happens to that milk after a little bit? What happens to my chocolate milk? What does the syrup do? Yeah, it starts to sink to the bottom. And so theoretically, my solution is not intact anymore, right? So we're going to keep stirring it and drinking it. No good, right? But when normal people make chocolate milk, your syrup doesn't fall out, right? It's not saturated enough to fall out. So its solution stays intact. So although something might be a solution at one point, it might not always remain a solution. Same thing if lemonade sits in your fridge too long, you see the sugar sink to the bottom. It's the same type of thing. Okay, so theoretically, solutions won't separate. These two vocab words, solvent and solute, you need to know those. Okay, solvent is what's doing the dissolving, and solute is what's being dissolved. Okay, so in our like chocolate milk and chocolate syrup example, what is my solvent? What's my solvent? So I've got a glass of milk and I've got my syrup. Which is my solvent? The milk, and the syrup that I pour into it is my solute. Right? It's what's being dissolved or being mixed up. Okay? So I'm going to demonstrate the correct way to make a chemical solution. So we've been talking about household solutions, but now I want to demonstrate steps for making a chemical solution because it's a little bit different. Okay? So what I want to do is we're going to make a solution of salt water. And I want to make a really exact solution of salt water. And so I'm gonna make in a certain concentration. Okay, we haven't gotten to concentration yet. We're gonna get to that later today. And so, actually, I'm gonna wait for that. Okay, we're gonna hold this off for a second. We're gonna do that when we get to talking about the concentration. So I'm gonna give you step by step of how to make a chemical solution the correct way in a little bit. Okay, so of these two objects, which is the solute? The Kool-Aid, right? Solute is the Kool-Aid and solvent is the water. Water is what we call the universal solvent. Like almost everything dissolves in water. Not everything, but a lot of things dissolve in water, and a lot of solutions are water-based. Okay? Can you think of some things that don't dissolve in water? Metals. What'd you say? I can't hear you. Rocks, okay? Minerals, some minerals. What other things don't dissolve in water? There's one. What did you say? Oil. Yeah, there we go. That's what I was looking for. Okay, there's a lot of things that don't dissolve in water, but yes, those are some of them. Okay, so typically the substance in greater proportion, or the thing you have more of, is your solvent. The thing you have less of is typically your solute. Okay, that should be pretty self-explanatory. I don't think picking out solvent and solute are really usually difficult things for us. Okay. When something becomes dissolved in water, we call it an aqueous solution. An aqueous solution means it is dissolved in water. Okay, when we put something into water and we see it dissolve, we see a process called ionization happening. Okay, and so water is what we call a polar molecule. And we're going to get into polarity a lot more later in the semester, but a polar molecule means that when I draw water, I've got electrons in these bonds. And a polar molecule means that the electrons within my water atom are not shared evenly. They're not dispersed evenly. They are gravitating toward one element or another. And so in this particular case, they're gravitating toward oxygen, right? The electrons are being pulled toward oxygen. And this is, again, more than you need to know right now. But what happens in these polar molecules is that they create these little mini positive and mini negative charges called partial positives and partial negatives. So in this water molecule, hydrogen has a little partial positive. That's what that sign means, partial. And oxygen has a partial negative. So they're like mini charges, like half charges, right? They're not full, but they're like kind of charges. And so what those partial positives and partial negatives do is they attract other partial positives and other partial negatives, right? If I put salt into water, we've got these partial charges going on. And these salt molecules start breaking apart. So now I've got a positive sodium and a negative chlorine. And they start becoming attracted to the partial negatives and partial positives in water. Does that kind of make sense? Right? These charges, right? Negative charges attract positive charges and vice versa. So what happens is water is a polar molecule. It has these partial positives and partial negatives. So when ionic compounds, which your book calls salts, right? There's a whole category of salts which are ionic compounds. When they're put into water, they dissolve by breaking into ions. And I want you to view this on page 140. So open your textbook to page 140, and I want you to look at this giant picture of it, because it does it a little bit better than I do. That shows water molecules, which are the green and gray, right, being attracted to nope, I'm wrong. Water molecules are the red and blue. Sorry. And sodium chloride molecules, or salt molecules, are the green and gray. Okay, so do we see how sodium is the gray plus sign, and the chlorides are the negative green ones? We seeing what's happening there? So you've got this big hunk of salt that gets put into the water, right, which really is probably only a tiny little grain. But they are formed in that crystal lattice, right? Salt is an ionic compound, and it's formed in what we call the crystal lattice. And so it forms this grid that holds salt molecules together, okay? Positive charges and negative charges. Then when you put it into water, the water molecules start picking them off, right? The water molecule contains partial positives and partial negatives, and so they start separating these salt compounds into individual ions, and that's the process of dissolving. It starts breaking apart the sodium and the chlorine into its own individual. So now you've got a sodium that's positive and a chlorine that's negative, and it starts to surround them with its own individual water molecules. So do you see from the left side to the right side how they've been split apart and then basically attacked with water molecules? That's dissolving. That's what dissolving is at the molecular level. It breaks apart its compounds and it surrounds it with your solvent molecules. Okay? And so the reason so many things dissolve in water is because water is polar, so it has these charges. And so you might hear the term like dissolves like, and so polar molecules dissolve other polar molecules and things like that. But I want to watch I have a little demonstration about maybe the dissolving process. Okay. Okay, we're going to skip that for right now. So, when you put an object into water to dissolve, or you put it into its solvent to dissolve, it requires energy to break the bonds. Okay, so if I put in a salt molecule, and I want to start it dissolving, we've got to break apart those bonds, and water starts to do it. But I want you to think of a couple other ways that encourage the dissolving of a solution. What can we do to speed up the dissolving process? Yeah, Brogan. Stir it, right? We can stir. What else? Why does stirring help speed up the dissolving process? What do you think? Yeah.
Gets the particles moving faster.
That's right. It moves the particles faster, which causes more collisions, which causes the opportunity for hydrogen and oxygen to start pulling those molecules apart. Okay? What are a couple other ways that we could encourage the breaking of those bonds between sodium and chloride and encourage the dissolving? Yeah, we can heat it up. Right? We do that for, like, when you're cooking and you want things to dissolve, right? If you've got sugar and whatever going, you heat it up. And what does heating it up do? Yeah, heating it up adds energy, which again makes our particles move faster and faster and faster. And when particles start moving too fast, the bonds that hold them together break, right? So think about if you've got like a rubber band holding two things together and they're both bouncing back and forth, eventually that rubber band's going to snap, right? That's like a chemical bond. So if you've got too much motion between your two particles, your bond will break, and then it will allow water molecules to start encompassing those ions. Okay, does that part make sense? Any other manipulations you think you can make to help the dissolving process? Okay, so there's one more that I want you to think of, and it's pretty simple. But if you put in if you make a can of orange juice, right, frozen orange juice, you know what I'm talking about? Plop it into the pitcher. What happens? It take a long time to stir it up, right, for it to get going. No? Yes? Mine does. Right? When I put in a frozen can of orange juice, it's like this big chunk. And I stir it, I think it's good. There's still a huge chunk of it in there, right? What can I do to speed up the dissolving process? Yeah, I can mash it up. I can grind it. I can cut it. I take my solute and I put it in smaller pieces. So I physically manipulate my solute to basically increase the surface area, right? I want more surface area so that those water molecules can start encompassing them quicker. So by breaking my big chunk of orange juice into like little slices or just mashing it up, allows those particles to spread out quicker and encourages the dissolving process. So I guess the last thing you could say is cut or grind or mash, right? Some sort of physical manipulation of our solute that allows it to spread quicker, right? That's what we're getting for. All right, I don't want to talk about that. Okay. Here's some things that affect how much an object will dissolve, okay? And I'm going to talk about a few factors. So when I say solubility or soluble, soluble is an object's ability to dissolve in water, okay? If it's soluble, that means it can dissolve. So an object's solubility is like a rating. How easily does it dissolve? Okay. Some things that can increase solubility or decrease, if you have a solid and a liquid, right, its solubility increases with temperature. So we said if we heat it up, it's going to dissolve more, right? When we put sugar in water and we heat it up, put salt in water, we heat it up, it dissolves quicker. I'm going to give you a couple minutes to finish getting this kind of written down, and then we'll talk through why these things occur. So strong and weak electrolytes, we're going to just like scratch the surface on what electrolytes do. But there's a category of electrolytes based on its electrical conductivity. So whether or not it can conduct electricity. Okay? It's considered strong if it really conducts electricity well. It's considered weak if it doesn't. And if it's non-electrolyte, it doesn't conduct electricity at all.
What is an electrolyte?
So I'm gonna go into that just a little bit more in a second. Yeah, it has to do with if an object ionizes all the way or if it dissolves all the way in water. Okay, bless you. All right. So when we say conducting electricity in a solution, we're talking about does electrical current move through that solution easily or not? Right? Does electrical current move through the solution easily or not? And so the way that an object can move through a solution easily is if it has a lot of ions present. So if there are lots of ions present in a solution, it's considered a strong electrolyte because electrical current can pass through. Okay? Electrical current usually takes the form of electrons, right? So if it has ions within that solution, the electrons can travel. So when we talk about electrical conductivity, if we have a solution that has all these ions, right, as soon as an object is dissolved in water, the ions split, right? That means it's a strong electrolyte. If the ions split enough, that means electricity can travel through well, which considers it to be a strong electrolyte. So examples of strong electrolytes are soluble salts. And remember, salt is another word for ionic compounds. Oops. So a salt is anything that's a positive and a negative. Okay, and so we think of salt as sodium chloride, but salts themselves are ionic compounds. Okay, those are considered strong electrolytes. So sodium chloride is a salt, also called salt. That's a strong electrolyte. Okay? It said other examples of strong electrolytes are strong acids and strong bases. And so down here I have some examples of what acids and bases are. So again, I'm going to let you write it down and percolate with it a little bit, and then I'll walk through it, some points that I want you to see. All right, so an acid, we learned, is a proton donor, right? It means it will give away protons when mixed with anything, right? Acids are a proton donor. Does that term sound familiar? Acids are proton donors. So when you put a strong acid into water, and hydrochloric acid is an example of strong acid. If you put this into water, it becomes H plus and Cl minus, right? That means that it's ionizing. That's a strong acid, which makes it a strong electrolyte. So a strong electrolyte means it completely splits into positive and negative ions 100% of the time. And so things that do that are strong acids and strong bases. So it says if 100 molecules of HCl are dissolved in water, it produces 100 H plus and 100 Cl minus ions. Okay, every single one of those will break apart. The same thing is true for bases. So if I have a base like NaOH, right, sodium hydroxide is a base. Any base basically has OH in it. There's exceptions, but for our purposes, bases are ones that contain hydroxides, okay? And so if I put in sodium hydroxide, that means I'm going to produce basically an Na plus and an OH minus, right? That's what this means when we say it completely ionizes. And so strong acids and strong bases mean they break apart all the time, okay? That's really all you need to know about electrolytes right at this point, is that strong electrolytes totally dissociate or totally ionize. Weak electrolytes don't, right? Weak electrolytes, they produce few amount of ions. So you don't need to write down all of this. You just need to know that weak electrolytes, they don't completely ionize. Oops, sorry. They don't completely ionize in water. Okay, so if something is not 100% breaking into positive and negative ions, then it's not a strong electrolyte, it's a weak one. And then non-electrolytes would make up things that don't dissolve in water. So non-polar molecules, things like that.
They don't completely ionize.
Yep, they do not completely ionize. That's what weak electrolytes do. They do some, they ionize some of the ions break apart, just not all of them.
But strong do.
Strong breaks apart all the time into positive and negative ions. Okay, so does the terminology make sense? Ionize means to break into ions. So if we say it doesn't completely ionize, that means it doesn't completely break into ions, which doesn't allow electric current to travel through, which means it's a weak electrolyte. Okay? As molarity. Molarity is the most common form of concentration solution units. So molarity is the unit of solution concentration. Okay, it is a unit of solution concentration, and it's given with a capital M. Capital M means molarity or molar. Okay, the equation for molarity is moles per liter. So I write it like this: molarity equals moles per liter. Okay, and it's moles of solute divided by total liters of solution. Okay, moles of solute divided by liters of solution. And it would be written, or it would be like spoken. You'd say, I have a 2 molar solution of whatever, right? That's how you would say it. You'd say the concentration in those terms. I have a 2 molar concentration. So, we're going to try this problem first, okay? A 4 gram sugar cubes dissolved in a teacup that holds 350 milliliters of water. What's the molarity of the solution? Okay, so do we see what process we might have to go through? Right now, I have 4 grams, and I have 350 milliliters of water. So I'm going to have to do some conversions, right? What conversions will I have to do? I need to go grams to moles first, right? And I gave you the formula for sugar. So let's do that first. Because I can't put grams per liters, right? It's moles per liters. So I need to go grams of sugar, so 4 grams of C6H22O11 to moles. So I do my conversions in T-chart form, right? I know Miss Kuchno, I think, just puts a times right there. It's exactly the same thing. Is that right? Does she do them just like this? Times? Oh, she does the... Oh, perfect. Okay. Cool. Okay, so I use the T-chart method, so hopefully that looks familiar to you. If I want to get rid of grams and go to moles, what do? Grams goes on the bottom, moles goes on the top, and what does moles always get? The 1. Moles always gets the 1. So what goes here with grams? The molar mass, or what? Did she call it molar mass? Yeah? Okay, good. Molar mass or molecular weight or whatever. Okay, so we need to find molar mass of C6H22O11. That's what you need your periodic table for. We're converting from grams to moles so we can use it in our molarity equation. Okay, so on molar masses, I don't care. I pretty much round everything I can to a whole number. So carbon, yes. Hydrogen, yes. Oxygen, yes. All can be rounded to whole numbers. So I'm not so picky about that. For things like magnesium, 24.3, I keep it at 0.3, right? So it's up to you, but if it's not like 97, 98, 0001, then I keep the decimal. But if it's really close to a whole number, I round it. Yeah. Good question. So for molar mass, did you get around 270? Okay, in the ballpark somewhere, right? If you kept your decimals, that's fine. Like I said, I like to round to whole numbers because I just know that carbon is 12 and oxygen 16 and blah, 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 blah. So it's not really worth my time to put the 0, 1. I'm sure it's worth some people's time. It's not worth mine. Okay, so 4 grams to get to moles, what do I need to do? How do I get from grams to moles? Do I multiply? Do I divide? Do I add? What do? Divide by molar mass. So I multiply across the whole top, divide by the whole bottom. That gives me 0.0148 moles, right? And again, I'm not so big with significant figures. I know that you probably should be, and I'm just not, okay? So I round where I think there's a natural stopping point, okay? For the most part, 2 decimals, but if there's a natural stopping point, like here I went 8.1, I just am going to stop at the 8. So again, that is your... for right now, that's up to you. I'm sure that in college later you will need significant figures again, and I just don't do them, so maybe that's my fault, but I don't. Okay? So if I want to go now and plug it into my molarity equation, I have moles. My volume, is it given in liters or milliliters? It's given in milliliters. What do I need it in? Liters. So how can I convert from milli to liters? divide by 1,000. So if I go, you can do the T-chart, but hopefully we're a little bit past that now. 1,000 milliliters in 1 liter. So I move the decimal place 3, or divide by 1,000, and I get 0.350 liters. So now I've got the components for my equation, and I plug it in. So I say molarity equals 0.0148 divided by 0.350. And I got about 0.042 molar. Agreed? The unit for molarity is just a capital M. So we say our final answer is 0.042 molar solution. That's how we would read that. Okay, so it has a concentration of 0.042 molar. Okay. Questions? Okay. Why don't you try this one on your own? What's the concentration in molarity of a solution formed by mixing 10 grams of, can anybody name this for me? H2SO4? No, close. The hydrogen at the beginning tells us it's an acid. Anybody? What's this by itself? Sulfate, which means it is sulfuric acid. Good. All right, just a little review. Okay, so I have 10 grams of sulfuric acid with enough water to make 100 milliliters of solution. So try this one. Take my 10 grams and I divide it by 98 grams per 1 mole. That gave me 0.0102. And I take that moles divided by liters. Converting your milliliters to liters is super important. Okay? Make sure you're looking at that. We agree? Is that what you had? Raise your hand if that's what you got. If you didn't quite get that, do you have questions? Yeah. You got 1.02. Is that what everyone got? Oh. Okay. I'm wrong. Okay. Yep. I plugged in 1 divided by 98 in my calculator, so that's where the problem was. Sorry. Jake, did you do the same thing?
Yeah, I didn't do the second
Oh,
part.
I'm with you. Okay. So when we take 10 divided by 98, then we get the 0.102. And then we take that divided by 100. So, yes, you're right. I'm sorry. It should have been 1.020 molar. My bad. Okay? Questions? You can correct me if I'm wrong. It happens. Hopefully not too often, but it happens. All right. Let's try this one. All right, so this, what does 3.4 tell us? What is that? That's our molarity. That's our concentration. So we say 3.4 M equals moles, divided by liters. We can change that to moles. That's 78 grams. C3H8O, so 60 grams maybe? Is that what you had for molar mass?
Yeah.
60, okay, that's fine. Okay. 1 mole. That gave me, 1.3 moles. So how do I solve for my volume? How do I solve for liters? For some reason, this is a random, this equation doesn't say moles over volume. It says specifically moles over liters. So that's just something that you'll have to notice. Instead of like density, it says mass divided by volume. Liters is a volume, but it doesn't say volume. So it says moles divided by liters. So it's a reminder to you that you should always be in liters. Okay, but if I want to solve for this, what algebra do I need to do? Do I multiply these two things together? No. No, if I want to get liters by itself, I multiply by liters on one side, I multiply by liters on the other, then I divide by 3.4, then I divide by 3.4. So essentially what I did is switch those two places. right? We swap those two places. So I take liters equals 1.3 moles divided by 3.4 m, and I get my volume. .382 liters. You can change it to milliliters, but I don't really find a need to do that unless it's really small amount of liters, right? This would be 382 milliliters, but you don't have to. Okay. Any questions with molarity? Okay, very last thing we're going to do today, and I know we're pushing time a little bit, but we're going to talk about concentration of ions within it. And it's very similar to finding the concentration of the whole solution. Now we're finding the concentration of ions. So if we put something in solution and it ionizes, there's going to be a concentration of individual ions, not just a concentration of the solution. So it's very, very similar to solving regular molarity. You just take it one step further. Okay? So if I have a solution that has a concentration of 0.50 molar, okay, I have a solution that has a concentration of 0.5 molar cobalt 2 nitrate, right? That's what this is called. Okay, so what I want to do is I want to find the concentration of both cobalt ions and nitrate ions within that solution. Okay, so it gave me the concentration of the whole solution is 0.5 molar. And then when I put this into solution, I end up with a cobalt plus 2 ion and a nitrate minus 1 ion. Really, I have 2 of these. Right? Okay, do we see what I'm talking about here? When I put these into water, and it separates, it ionizes. That leaves me with a cobalt ion that has a plus 2 charge, and it leaves me with 2 nitrate ions, right? Because I've got that 2 right there. Does that part make sense? Give me like a yes or a no. Okay, when I put it into water, it splits. 1 cobalt, 2 nitrates. So when I want to find the concentration of just cobalt ions, if there is 1 cobalt ion for every main molecule, that means that my concentration of cobalt ions is just equal to 0.5 molar. Right? If there's 1 cobalt ion for every molecule of cobalt 2 nitrate, that means the concentration of cobalt ions is the exact same as the concentration of the total compound. It's a 1-to-1 ratio. Does that make sense? So what would the concentration of my nitrate ions be? If there's 2 nitrate ions for every 1 molecule of cobalt 2 nitrate, what would my concentration be? It would be close. You're thinking
It's like half of the 0.50.
almost. It's twice that, right? So if I have 0.5 molar concentration of my total system and I have 2 times the amount of nitrate molecules, that means I can say 0.50 molar of CONO3 and I can say 1 mole of my compound CONO3 is to 2 moles of nitrate ions, right? Because we have twice as many nitrate ions in that solution. So it's 0.5 times 2. So my concentration of nitrate ions is twice as much because I have twice as many nitrate ions. Okay, how do we feel about that?